If something were lurking in the cosmos that defied the fundamental laws we use to understand the universe, an invisible force or entity breaking the rules of space-time as we know them, it would be as elusive as it is essential to grasping the deepest mysteries of existence. The universe hides secrets that challenge our every perception, pushing the boundaries of reality and hinting at phenomena beyond imagination. It is a long story, but we shall begin in the realm of dreams. Before we start, don't forget to like and share. Physicists have long struggled with the twin mysteries of dark matter and light. At the intersection of these two domains lies an arresting concept, the dark photon. This hypothetical particle raises questions profound enough to reshape our entire worldview. The dark photon may serve as a bridge between the visible and invisible components of the cosmos, acting as a mediator between light and dark matter. As scientists delve deeper into its implications, they find its existence challenges the standard model of particle physics, the theoretical framework that has underpinned our understanding for decades. While the standard model describes the elementary particles and forces that govern the universe, the dark photon represents a new particle that refuses to fit neatly into this framework. This inconsistency sparks a tantalizing thought: could the dark photon reveal a fundamental gap in our current theories? If they exist, they would open the door to a new physics beyond our established knowledge. One of the most fascinating aspects of the dark photon is the proposed mechanism of kinetic mixing. This interaction allows dark photons to couple with the photons of the standard model, enabling indirect detection through observable effects on light. For example, scientists can look for shifts in spectral lines caused by this interaction. This idea has generated immense excitement because it provides a potential path to finally unveiling the secrets of dark matter. It begs the question: is the dark photon the key to the ultimate puzzle of particle physics? The answer may lie in the experimental discoveries of the coming years. Furthermore, researchers are exploring how dark photons fit into models of dynamical dark matter. Traditional models treat dark matter as static, but dark photons suggest a more dynamic approach where dark matter evolves over time. This has significant implications for our understanding of cosmic structure formation, potentially explaining the large-scale structures we observe today. These dynamic models challenge established notions and push astrophysics to rethink the evolution of the universe. Looking back at the early universe, dark photons also appear relevant. Their interactions may illuminate the period of inflation, that era of violent energy fluctuations following the Big Bang. If dark photons participated in this cosmic expansion, they could rewrite our understanding of how energy dynamics shaped the evolution of the cosmos, offering a glimpse into the very fabric of the universe. Researchers are not stopping at theory, they are hunting for observable consequences. One exciting area is exotic decay channels, where dark photons might allow dark matter particles to transform into standard model particles that our future experiments could capture. This prospect points to an undiscovered treasury of phenomena. In analyzing astrophysical data, dark photons might also explain several anomalies, such as the excess signals in cosmic rays or gamma rays that baffle researchers and do not fit current interaction models. The dark photon could be the missing puzzle piece for these unexpected observations. Another intriguing direction involves the cosmic microwave background, CMB. Dark photons could influence the patterns we observe in the CMB through their interactions, leaving a detectable imprint that helps us solve the dark matter mystery. Understanding the CMB is crucial to cosmology, and dark photons may play a key role in enhancing our grasp of cosmic history. Neutrino physics also stands to benefit. The interactions of these elusive particles may be linked to dark photon behavior, revealing new insights into this mysterious branch of physics and showcasing the intricate web of interactions in nature. Turning to gravitational interactions, dark photons present fascinating prospects. Under specific conditions, they might decouple from electromagnetic forces to produce unique gravitational behaviors. How would this affect our understanding of gravity? The implications are vast, suggesting that the fabric of space-time might be influenced by these interactions in ways we do not yet fully comprehend. This exploration may even reveal links to gravitational waves. Researchers are investigating how dark photons might affect the generation or detection of these ripples in space-time, particularly in events involving massive objects like merging black holes or neutron stars. Plasma filaments constitute the invisible highways of the universe, weaving through the vast cosmic landscape, yet they often remain unseen. Imagine navigating a city where the main arteries are hidden by buildings and alleys. These filaments are the hidden roads connecting galaxies into a dynamic network, influencing the very limbs of the universe. They are not empty voids but conduits of energy and matter, guiding the flow between galaxies. These filaments act as channels feeding gas into galaxies, which is vital for the birth of new stars, making them key protagonists in the story of cosmic evolution. Tracing the origins of these filaments leads us to baryon acoustic oscillations, BAO, sound WA. Dictated where filaments would form, influencing their behavior and interaction with surrounding matter. Magnetic fields add another layer of complexity. They permeate the universe and influence the behavior of charged particles, playing a critical role in regulating star formation rates and shaping the life cycles of galaxies. Temperature variations within these filaments are also vital. Gas can reach extreme temperatures, driving flows and triggering the creation of active stellar nurseries. This dynamic interplay is key to understanding galactic evolution. The relationship between plasma filaments and dark matter is equally captivating. By studying how filaments interact with dark matter, scientists can map its distribution and influence, helping us piece together the puzzle of this elusive component. Astronomers use advanced radio telescopes and X-ray observations to analyze these structures, providing details that enrich our understanding of cosmic dynamics. Numerical simulations play a crucial role here, predicting how filaments behave and interact over time. These models provide insights that observational data might miss, allowing us to see the delicate processes carving the universe's structure. When galaxies pass through plasma filaments, they trigger shock waves that heat nearby gas and alter the conditions for star formation. Furthermore, plasma filaments contribute to gravitational lensing, where the light from distant galaxies is bent. By analyzing these distortions, researchers can map the distribution of mass in the universe. The Eridana supervoid is a striking cosmic anomaly of vast regions spanning roughly 1.8 billion light-years, about 6 times the diameter of the Milky Way. Its sheer scale poses serious questions about the distribution of matter. Why is there a region so devoid of galaxies and structure? This is not just a small gap in the cosmic web, it is a gargantuan empty room where galaxy clusters should be. Some scientists propose that the supervoid formed through gravitational interactions over billions of years, as matter was pulled away toward higher density regions. This supervoid significantly impacts our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. By observing how light from distant galaxies traverses this void, researchers gain valuable clues about the nature of dark energy. This discovery also challenges existing cosmological models, which assume matter is distributed relatively uniformly on large scales. To explain the Eridana supervoid, cosmologists may need to revise their simulations and theories, potentially leading to a revolutionary shift in our understanding of cosmic evolution. Research has found that the void is not absolutely empty, though the density is significantly lower, it still hosts faint, distant galaxies. Interestingly, these galaxies seem to have weaker star formation capabilities, suggesting that evolution in such a thin environment differs from high-density regions. Furthermore, galaxies on the edge of the void may exhibit anomalous motions due to the void's unique gravitational influence. Using advanced radio telescopes and deep sky surveys, researchers are gathering data on how the supervoid interacts with the CMB, shedding light on its role in shaping the universe since its earliest moments. Ancient megamasers emit powerful radiation from hundreds of millions or even billions of light-years away, opening a window into cosmic history. Often associated with distant galaxies, they act as beacons illuminating secrets buried for eons. Their molecular composition is peculiar, consisting primarily of molecules like hydroxyl, water, and formaldehyde, which emit intense radio waves. The unusual molecular composition of megamasers is more than just a cosmic curiosity, it is a vital clue for understanding the chemical evolution of galaxies. These ancient, naturally occurring lasers harbor revelations about the early universe. Megamasers act as cosmic time capsules. When we observe their radiation, we are looking back billions of years, gaining a front-row seat to how galaxies first formed and evolved. Every pulse carries data from the universe's formative years, telling us which processes sculpted the cosmos we see today. Many megamasers are found in starburst galaxies, regions where stars are born at an explosive, frantic rate. Understanding the link between these cosmic lasers and such high-energy environments helps reveal the fundamental drivers of star formation and energy output. Perhaps most fascinating is their connection to supermassive black holes. Many megamasers are located near active galactic nuclei, AGN, suggesting that the influence of a black hole on surrounding molecular gas is what triggers these powerful beams. Megamasers also serve as the universe's mile markers. They allow us to measure galactic distances with staggering precision, helping us refine the Hubble constant, the rate at which the universe is expanding. Their stable radiation provides astronomers with a high-precision cosmic ruler, essential for clarifying the mechanisms of cosmic growth. Among these, hydroxyl O megamasers are particularly rare, often signaling the violent collision of two galaxies. Meanwhile, water $H_20 megamasers are incredibly robust. Water molecules near a supermassive black hole can produce beams that remain detectable across millions of light-years. They even offer clues about dark matter as their light passes through certain regions. Scientists can study how invisible gravitational forces distort the signal, providing an indirect way to map the unseen mass of the universe. The solar corona remains one of the most puzzling structures in our solar system. Extending millions of kilometers from the Sun's surface, it presents a staggering paradox. Why is the corona significantly hotter than the surface of the Sun itself? While the solar surface sits at about 5,500 degrees Celsius, the corona can soar to over 3 million degrees. This vast temperature inversion suggests complex, hidden processes within the solar atmosphere. The leading hypothesis attributes this extreme heating to magnetic fields. The Sun is a dynamic engine, and the corona is filled with visible magnetic loops and arches. These structures can store immense energy and release it suddenly through a process called magnetic reconnection. Could this be the master key to the mystery? Additionally, the Sun's internal convection produces acoustic and magnetohydrodynamic (MHD) waves that travel upward, dissipating their energy into the corona. Missions like SOHO and the Parker Solar Probe are essential to solving this puzzle. These spacecraft provide unprecedented, close-up observations of the solar atmosphere, and the data they collect is constantly refining our models. Another critical factor is coronal mass ejections, CMEs, massive bursts of solar wind and magnetic fields that inject enormous amounts of energy into the atmosphere, momentarily altering its structure and temperature. Understanding the relationship between CMEs and the corona is vital not just for solar physics, but for protecting Earth's technology. Space weather can disrupt satellites and communication networks. By mastering the behavior of the corona, we can build better forecasting models to safeguard our infrastructure from solar storms. Axions are among the most enticing possibilities in modern physics, bridging the gap between particle theory and cosmology. If they exist, they could fill a critical void in our understanding of dark matter. Though notoriously difficult to detect, their potential impact on cosmic evolution makes them a central key to unlocking the mysteries of the invisible universe. The Axion mystery began with the strong CP problem in nuclear physics. According to quantum chromodynamics, QCD, the strong force should violate certain symmetries, yet observations show it doesn't. In the 1970s, the axion was proposed as a way to naturally explain the symmetry. But if axions solve a problem in particle physics, how do they relate to dark matter? Dark matter doesn't emit or absorb light, yet its gravitational hand is everywhere, shaping how galaxies rotate and how light bends around clusters. Because axions are extremely light and interact very weakly, a cloud of them could gently sculpt the gravitational profile of the universe without being seen. One clue comes from white dwarfs. These ancient stars are cooling faster than our current models predict, leading astrophysicists to suspect that axions might be carrying energy away from their dense cores. If axions are escaping from stars, they might be subtly influencing the entire life cycle of stellar evolution. Experiments like ADMX are currently trying to catch axions by using strong magnetic fields to convert them into detectable photons. However, the challenge remains: are we looking in the right place, or are their properties just out of reach of our current sensitivity? Neutron stars provide another laboratory. If axions are produced in their hyperdense cores, the resulting energy loss would change the star's observable properties. Furthermore, axions might be linked to the Hubble tension, the disagreement over the universe's expansion rate, by influencing the amount of dark energy and matter over cosmic time. Even supermassive black holes might be axion factories, where the black hole's spin interacts with an axion field to create a detectable signal. The first quasars are among the brightest and most mysterious objects in the universe. Appearing only a billion years after the Big Bang, they tell a story of a chaotic, burgeoning cosmos where the first galaxies were just beginning to take shape. Driven by supermassive black holes at their centers, these early quasars provide a glimpse into the conditions of the infant universe. What is truly shocking is how quickly they formed. Growing a supermassive black hole usually takes billions of years, yet these early quasars reached staggering scales in a very short amount of time. One revolutionary explanation is the direct collapse hypothesis, which suggests that massive clouds of gas collapse directly into black holes, skipping the traditional stages of stellar evolution. These quasars acted as the flashlights of the early universe, ionizing the surrounding neutral hydrogen and making the cosmos transparent to light, a period known as the epoch of rionization. If this theory holds, we can finally understand how the infant universe, in just 1 billion years, could nurture such gargantuan entities. Quasars played a pivotal role in the cosmic rionization. After the Big Bang, the universe was shrouded in a thick fog of neutral hydrogen. As the first stars and galaxies ignited, their photons began to ionize these hydrogen atoms, allowing light to travel freely across the void. The intense ultraviolet radiation from quasars was a primary driver of this process. Without them, the universe might have remained dark and opaque for far longer, significantly delaying the birth of structural complexity. Quasars are also indispensable tools for modern astrophysics. Their light travels across billions of years of space-time to reach our sensors. By analyzing the absorption lines in their spectra, the chemical fingerprints left behind when light is absorbed by intervening gas clouds, we can reconstruct the chemical composition and temperature of the early universe. This allows us to map the distribution of large-scale structures from an era we could never otherwise see. Despite their terrifying energy output, some quasars are remarkably long-lived, raising new questions. How do they maintain their fuel supply over eons? One possibility is that they are intermittent, flickering to life when they encounter a new reservoir of matter and then slipping into a dormant phase. The impact of a quasar on its host galaxy is profound. Their powerful winds and relativistic jets can strip gas away, suppressing star formation in some cases, while in others, they compress gas clouds to trigger a burst of new star births. This dual role, both a destroyer and a creator, makes quasars the ultimate architects of early galactic evolution. Furthermore, Heavy elements like carbon, nitrogen, and oxygen have been detected in the spectra of the earliest quasars. This implies that even before the first quasars lit up, the universe had already cycled through generations of supernovae, enriching the interstellar medium and setting the stage for the complex chemistry required for life. Saturn's largest moon, Titan, has long captivated scientists with its thick nitrogen atmosphere and vast methane lakes. What makes Titan truly fascinating is the complex organic chemistry occurring in its upper atmosphere. This region acts as a unique chemical reactor, where solar radiation and cosmic rays interact with simple molecules to produce exotic organic compounds, including polycyclic aromatic hydrocarbons, PAHs, and complex ions. These reactions mirror the prebiotic chemistry that may have occurred on the early Earth. In Titan's upper atmosphere, researchers have detected unexpected ionized molecules, including large positively charged ions that differ from those found in typical planetary atmospheres. These ions are likely the precursors to the organic aerosols that form Titan's characteristic orange haze. One molecule in particular, acrylonitrile, is of immense interest. It could potentially form stable membranes in liquid methane, mimicking the function of a cell membrane. This invites a thrilling question: in an environment so different from our own, what would life look like? Titan's nitrogen isotope ratios differ significantly from Earth and even the Sun, suggesting its atmosphere's origin is far more complex than we once thought, perhaps delivered by comets or captured during the early stages of the solar nebula. Even in the extreme cold of -179 degrees Celsius, molecules like hydrogen cyanide can link together to form long chains similar to the building blocks of life. Additionally, Titan features a complex hydrocarbon cycle where ethane clouds condense and rain down to feed lakes and riverbeds. This world serves as a natural laboratory, offering a glimpse into the prebiotic Earth and showing us how life's precursors might emerge under conditions that seem utterly hostile. Tidal disruption events, TDEs, provide a unique window into cosmic dynamics, specifically the violent interaction between a star and a supermassive black hole. When a star wanders too close to a black hole, the immense tidal forces stretch it until it is literally torn apart, a process known as spaghettification. The resulting debris forms a stream of matter. Some falls into the black hole, while the rest orbits it, forming an accretion disk that can glow brilliantly for months or even years. These events are a primary mechanism for black holes to accumulate mass in otherwise quiet galaxies. The brightness and visible signal of a TDE are dictated by the star's initial trajectory and orbit. In some cases, TDEs even produce relativistic jets, high-energy beams blasting from the black hole's poles, revealing the intense magnetic environment surrounding the event. By analyzing the light curves of these events, scientists can even infer the spin of the black hole, a measurement that is otherwise nearly impossible to obtain. Furthermore, the spectra of TDEs carry the chemical fingerprints of the destroyed star, giving us a rare look at the composition of stars in distant galactic centers. In some scenarios, the core of the star might even survive the ordeal, being flung away at high velocities as a zombie stellar remnant. Finally, we look to the black dwarf, a conceptual ultimate remnant of stellar evolution. These are the final husks of white dwarfs that have cooled over trillions of years until they no longer emit heat or light, becoming virtually invisible. The formation of a black dwarf is a journey of heat loss so slow that the universe is currently too young for a single one to exist. Theoretical estimates suggest the process takes 10^15 years. Searching for these invisible remnants requires creative methods like gravitational microlensing, where the gravity of a black dwarf subtly bends the light of a distant star. While white dwarfs start their lives hot and bright, their transition to darkness is a delicate dance of thermodynamics and quantum degeneracy. If black dwarfs exist in significant numbers in the deep future, they will reshape the gravitational landscape of galaxies, affecting the orbits of nearby stars and gas clouds. Unlike the violent end of a supernova, the black dwarf represents a silent, peaceful finale to a star's life, a testament to the incredible diversity of stellar destinies. Our journey through the cosmos, from the brilliant quasars of the dawn of time to the silent black dwarfs of the far future, shows a universe defined by the interplay of light and shadow, the visible and the invisible. That concludes our knowledge sharing for today. I wish you wonderful dreams and a beautiful day ahead. We'll see you in the next episode.